Alrighty, so in this first video with GDC skills for IB, we're going to have a look at topic 1, and we're starting off with 1.1, and that is that you're expected to be able to put numbers in scientific notation. And the reason why I'm stopping here for a second is just to remind you guys that calculator speak is never okay in your exams. Okay, so it's not okay to write 5.23 5.2 E30. It should be written as 5.2 times 10 to the power of 30. So I'll just give you an example on the calculator here. You can see I've got 12.3 times 10 to the 12, and it has returned it as 1.23 E13. So just a reminder that in scientific notation, it's normally a number between, I think it's between 0 and, or is it between 1 and 10, is it? I was thinking it was between 0 and 10. No, between 1 and 10, not inclusive of 10. So you can see that the calculator will naturally put it into that notation already. And because you can see that it says E13, not 12, because the decimal place has gone back 1 to make it into a scientific notation appropriate thing. So just be mindful of that. The calculator might give you 1.23 E13, but you will write down 1.23 times 10 to the power of 13. So you put it in that notation. Any questions about that? Okay, so that was not a how to use a calculator, but just remember your calculator, you are expected to interpret calculator questions. Okay, I feel like I don't need to do this on the calculator. Arithmetic sequences and series, the use of the formula. There's nothing special about the calculator other than just being able to use it, to press the right buttons for stuff. You could technically create functions if you had a question which required you to interrogate. If you thought that perhaps you were going to be using it over and over again, you can go F1 of n and then use the becomes equals, colon equals there. And let's just say A1 was 12. So it's A1 plus n minus 1. Oops. N minus 1 times d. Let's say the difference was negative 2. Got to use the right negative. Not that one. Where is it? Here. Multiply by negative 2. Might even put it in brackets because I'm getting really antsy about negatives. So you could set an arithmetic sequence like that in your calculator, and similarly for a geometric sequence, so that if it said, what is the 100th term? Boom, done. So if you're looking at I'm thinking of the longer form questions where there might be multiple parts to it, then it might be quite useful. Do know that it is a function, so I can go f1 of 0, and that is not the first term. That would actually be the term before the first term, which doesn't exist, kind of thing. It's a function. It exists as a function. You can do f of 1 of 1.5, and that doesn't actually make sense in the context of an arithmetic sequence. But keeping all that in mind, you can create the function so that you're going to get the outputs as expected. And you can do reverses as well. You've got nsolve. So f1 of n equals which term? When does the term get below negative 1,000? Something like that. You could do that. Oops. Comma n. Oh, I didn't mean for that to be accurate. So there you go. So it would be the 507th term when it gets to negative 1,000. So you can use things like that. And of course, you could graph it if necessary as well. But just remember, you're looking at a continuous function here, whereas arithmetic and geometric sequences are discrete functions. They only take on integer values as the input. They don't have decimals. So if I go in solve F1, I'll try and force it to give me a solution. Equals negative 1,001. There you go, 507.5, for example. If you would never write that down, you would say, well, n would be 508 when it breaches 1,001, or whatever. Does that make sense? So you can use GDCs in that fashion. Is this useful? Pointless? All right, okay. The other thing I thought would be worth looking at, I don't think we need to look at simple interest, do we? But when we look at geometric sequences, they often talk about, there's often some financial maths in there, sort of thing. So are you happy if I have a quick look at a financial maths problem? I think it's actually 1.4, but yeah, it's all in the geometric stuff. So I've actually gone to Revision Village just because it's too difficult to work out a solution otherwise. Just zoom up a little bit. No, it's not going to let me. So the question is, on the 1st of January 2021, Fiona decides to take out a bank loan to purchase a new Tesla electric car. I hope Tesla got a kickback for this exam. Fiona takes out a loan of P dollars with a bank that offers a nominal annual interest rate of 2.6% compounded monthly. And the size of Fiona's loan at the end of each year follows a geometric sequence, which we know. This could be entirely done using geometric sequences. Okay, you could just set it up as a geometric sequence and solve it, but it is also entirely legitimate to use the financial solver, which is what I thought I might just very briefly do. So we can see, well, I'll show you where to find it first. I'll switch between screens a bit so you can see it. So under menu, you've got number 8 Rooney there, which is finance, and then you've got the finance solver. I think this is really the only one I've ever bothered to use in this course. There are other stuff here. I don't even know what they do. I haven't really looked at it. You're basically putting what you do know, and it will calculate what you don't know. That's how it works. So in this case, we've got the principal value of P dollars. We don't know that. We'll just leave that blank. We've got the interest rate at being 2.6%. So not 0.26 or 0.026, but literally 2.6. It's expecting a percentage. PV is a thing we don't know. What else do we know? We are told find the value of A. What was A? Oh, the common ratio. Okay, so we need to, or alpha, by the looks of it, they've used. So we're looking at a period of 1 year, which is why you've got K equal to 12. That's the payments per year of 12 over a single year. So I've got to go back here and do 1 year because I forgot about that. So we're just doing it over 1 year because we're just trying to work out what that ratio is. We don't need to be any more fancy than that. And what else? And then the final value is, oh, we don't know that either. Maybe I should have gone through the formula first. 1.0263. This might not give it to us. Hang on. Yeah, maybe have I missed something here? It takes out a bank loan. Doesn't say how much. We know it's P dollars. We need to work that out. Compounded monthly. Yeah, maybe I should have actually looked at this a bit more carefully. Yeah, sorry. I should have read the question more carefully. I don't think we can do it. I'll go out of the thing so you can see a bit better. So the point with this, which I just didn't realize, sorry, my bad, is that you've got, sorry, it's a bit small, but this is the initial value, which is just P, and the final value after 1 year would be P multiplied by alpha, like the ratio, right? So it'll be 1 point something, right? Because if she doesn't pay anything back, then there would be a certain amount of money that would be accrued over the year, right? So the approach then would be to use the formula to then work out that the final value is whatever the first value is multiplied by a figure, and that's what we don't have. But you can see what I'm effectively going to do is I'm going to divide out the p's here. So I'm going to have 1 plus 2.6 multiplied by 100 times 12 over 12 times 1. So I think, I could be wrong, because I'm just, like I said, this video is a bit dodged because I'm just making it up as I go along. I think we could say the PV is 1, and then the final value after 1 year would be 1.002. Is that right? It's not right, so I'm not thinking it through straight. So I wish I could just zoom up, and I can't. But that's the approach. Sorry, so it didn't really use the calculator in this case. It just used the formula for compound interest, and then the trick was to know that your sort of the proportion will be p times alpha on the left hand side, and then you've got p on the right hand side. You're dividing out the p's and solving there. So sorry, that was a bit of a washout, that particular example. But let me just say, for example, I'll just make it up then, just so you can sort of get a sense of it. So if you had this kind of question and it was said, how much would, if the car cost $75,000 and she made no repayments, how much would she owe after 3 years? That's how you would do it. You would say 3 in here for N, 2.6, $75,000, and then you will say 0 for payment, and then the final value, you just press enter, and that's what it will be worth, $75,488 after 4 years. Sorry, after 3 years. That's how you use it. Or instead you can say how much, when will the loan be over $100,000? So you go minus 100 because you owe, minus $100,000, and then you could go back up to N and press enter, and you can see it would take you 132 years before it got to $100,000 at that interest rate, where you've got 12 payments per year, effectively. Okay, no, that's not right. That's right. That's why it wasn't working. Thought it looked a bit dodgy. Yeah, 11 years. That sounds a bit better. Okay, so that's basically the approach here. Just really quickly, let me just see whether what I had was going to work anyway. Yeah, it did work. So I thought I was right. So what I did to solve this actual question using my financial calculator is sort of said, well, to work out the ratio, I know the ratio will be as if the principal was like $1. Then the end result would be what the ratio is, because 1 times the ratio would be p times alpha. So I just put in p initial value of 1, and the FV would be alpha 1.02 or 1.03. There you go. That's how you do that. Yeah. So basically, you can do. I think you can calculate a whole bunch of things. You can calculate the final value given a principal value or present value. I think you can work out interest rates as well, and you can also work out the number of payments required just by filling in the information you do have and letting the calculator work out the rest of it. So here is how often you get paid the interest, I suppose, and this is how many compounding periods you would have. So if you've got N here, and if you've got N in years, then PPY would be 1, and then compound the CPY is how many times it gets compounded over that period of time. So if it was monthly, it'd be 12. If it was fortnightly, it'd be 26, etc. Okay, so that's a really rough, because I stuffed up the example I had, a really rough idea of how to use the financial solver. Does anyone have any questions on that? Faster. If you know how to use it, it's faster. This was, I cannot emphasize enough, Siggy, that the example that I quickly found that would illustrate it was like one of the worst examples I could find. So I wouldn't use it for this. And I'm not going to waste any more of your time or the video's time finding an example. It's really hard for me to make up on the spot. But it's the kind of problem where it might get you to compare. It might say something like, investing money, and it might ask you to get you to compare compounded monthly versus compounded daily. And so you could go quickly into your finance solver and put in all the details, and go compounding per period year is 12, and then redo it again with compounding periods per year being 365, and it really quickly gives you the answers, if that kind of makes sense to you. So that's the kind of thing you'd use it. And please note that the way they've got this set out here with PV, RKN, that kind of thing is absolutely legitimate, which is weird, really, since they say you're not supposed to talk in calculator speak. And I always feel like this kind of table looks like a calculator rather than what you would do in regular old maths. But nevertheless, they are happy for you to literally write down the headings here and then solve it from there. Have you checked in at the office? Great. All righty. So I'll move on unless people have any more questions. Yeah, sorry about the example. That's what I get for doing it on the fly. I never get rewarded for just doing things on the fly. Never goes, yay, perfect. Yeah, I do get rewarded sometimes, I'll be honest. Laws of exponents with integer exponents, introduction to logarithms with base 10 and base e. I don't think I need to do anything like that. Most of these things are laws that are on your formula sheet, nothing to do with your calculator usage as such. The only thing I will say is, does it go on here? Yeah, back here, is that these sorts of knowing your logarithms to the extent that you can manipulate your equations to use them on your GDC is useful. I'm going to come back and talk about change of base theorem in a second. All of these sorts of things you should be able to do manually, these examples here. But if you've got something like 2 to the power of x minus 1 equals 10, there's a couple of things you can do, really. You can use nsolve. 2 to the power of, what was it? X minus 1, I think, equals 10 with respect to x, and it will give you that as well. Sometimes the solutions, remember that the problem with numerical solve is that if there are multiple solutions, it's only going to give you one. So just be careful of that. So I'm going to do a slight bit of board work here, which is going to be great for the video. But the other thing you can just keep in mind is that if you've got 2 to the power of x minus 1 equals 10, for example, you should be pretty solid with using change of base to go, changing into base form to say it's log base 2 to the power of 10 equals x minus 1. So x equals 1 plus log base 2 to log base 210, which, to be honest, if that was the whole question, which it almost definitely wouldn't be, that's good enough. That's an exact answer. Perfectly fine. But if it was part of a bigger problem where you needed to decimalize it, because you've now turned it into a log, you can go log plus control log, or control 10 to the x. There we go. And we'll put in the base of 2. And we'll go put in 10 here. And unsurprisingly, it gives me the same answer here as well. Okay, so both of those approaches would work. And there's nothing wrong with you. Oh, no, I won't say that. Yeah, so you can do one or the other. You can do the change of base yourself, or you can go straight for an nsolve. So what will give it away as to which approach to take is, like, if this was part of a bigger question, if this was I of part A and it was worth 1 mark, maybe, sorry, just nsolve it because it's only 1 mark. They're not going to be looking for anything for 1 mark. But if it was worth 2 marks, you'd probably want to do something to make it worth 2 marks. So you do a little bit of manipulation to get x equals and then use your GDC. Now, what happens if you get to the exam and your GDC isn't working as it should do, or is flat? Oh, sorry, that was a rhetorical question. Um, it's almost definitely not going to happen. But the point is that you got your scientific calculator, so you can still do a bunch of things, just not the things that require a GDC. So I think it's important to know that it's under those sorts of circumstances where a change of base logarithm could be useful for you. So you can see log base AX equals log base B X over log base B A. So I can change log base to 10 to a different base. So I can go 1 plus 1 plus, for example, ln. You've got an ln button on your calculator and you've got a log button on your scientific calculator. You might not have a log base on your calculator. So I can go ln 10. So remember, ln is natural log base e, over ln of 2. And again, it's the same answer again, change of base theorem. So make use of that. The other thing I'll say as well, just while I'm thinking of it, is that I'm just looking at that notation there. You can, if you've got a sort of a complicated expression that you're trying to, like 1 plus 2 divided by 3 minus 4, if you put brackets around it, it'll be fine. It will convert it like that. Don't forget divisions, or particularly complicated divisions, can be put straight into fraction form by going control divided by, and then you can just put the top and the bottom in as it says on your calculator. So just keep that in mind. I think that's all I need to say with this kind of problem. I can do this one as well just to show you. A third to the power of x equals 9 to the power of x plus 1. Now, that's something you should be able to do without a calculator anyway. But again, just for proof of purchase, you could use nsolve. I can then go control divided by, probably have brackets around the whole thing, 1/3 close bracket to the power of x is equal to 9 to the x plus 1, 9 to the power of x plus 1, comma x to say what I'm solving it in relation to, and there you go, and probably reinterpret that as x being minus 2/3. You can see that from the decimalisation, I hope. I think, I can't remember what on a CAS calculator, but I think, non-CAS calculator, I think it will allow you to approximate the fraction as well there. Minus 2/3. Okay, so again, menu, number, and you can see there's a bunch of things there. You can find LCM, GCD, you can factor something. I think it does it into prime factors from memory, etc. And I think most of these, I'm pretty sure most of these are, no, all of these are turned on for your exam when it's in press to test mode. Anything else on logarithms you want me to have a look at in terms of GDC work? Note this as well quite often, and I thought I just wouldn't do that in this video, but you can often solve things, remember, by taking your logarithms and setting it equal, whatever your expression is, setting it equal to 0 and solving, and then graphing the left-hand side and looking at x-intercepts as a really powerful way of finding multiple solutions where necessary. And what else? Nothing the GDC will help you with here, other than you can use your GDC to store a geometric sequence in, but these are infinite ones anyway, so it's not really GDC work. GDC for the binomial theorem and NCR notation. I guess just to remind you where it's found, menu, probability, because it's a probability concept really. There's factorial there, and there's combinations there. There's the only two you need to know. Personally, I don't know whether it's just because I'm doing it on my laptop, but I think it's faster just to type in NCR, and then you can go 12,4, and there would be your starting coefficient for a power of 12 expansion, fifth term along, that kind of thing. Again, I'm not trying to teach you how to do the binomial theorem, just reminding you of the GDC bits. And if you do need factorial notation, There is, I thought there was a factorial here somewhere. Is it under here? No, I'm sure it's there somewhere. Oh, down there. Yep. So if I type in 0 factorial, what am I going to get? Bzz, bzz, tick. Who said 1? Yep. And I won't explain why now, but 0 factorial is actually can be proven to equal 1, but what we tend to say to students is it's defined as 1. 0 factorial is 1. Just for you, Zoe, I'll find a little video that explains it. Okay, that is that. Anybody got any questions about the GDC usage for this kind of stuff? There's no real way of, because it's a non-CAS calculator, there's no way of expanding that other than by using NCR notation or using Pascal's triangle. Okay, and I think that's it. So it's 9:25 with 5 minutes to go. I'm going to stop the video.